When dealing with parallel conductors in an electrical system, particularly in a scenario like a 1000 amp main distribution panel or MDP, where you are paralleling three sets of 500 mcm conductors, it is crucial to understand the equipment grounding requirements as outlined by the National Electrical Code, or NEC. The fundamental principle to remember is that an equipment grounding conductor, or EG, must be installed in each raceway or cable containing the parallel circuit conductors. In your specific case, where you have three pipes, each containing a set of parallel 500 mcm conductors, you are required to install an equipment grounding conductor in each of those three pipes. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This, in turn, helps to minimize the risk of electrical shock and fire hazards. Now, let us delve deeper into the reasons and code references that support this requirement. The NEC addresses parallel conductors in section 310.10. This section outlines the conditions under which conductors can be run in parallel. When conductors are run in parallel, the code mandates that the equipment grounding conductors also be run in parallel. NEC section 250.122 provides the requirements for sizing equipment grounding conductors. This section indicates that the size of the equipment grounding conductor is based on the size of the ungrounded conductors. However, when conductors are run in parallel, the equipment grounding conductor for each parallel set must be sized based on the equivalent size of the parallel conductors. To illustrate this with an example, consider that you are using three 500 mcm conductors in parallel for each phase. To determine the equivalent size of the parallel conductors, you would add the ampacities of the three 500 mcm conductors. Then, you would refer to NEC table 310.16 to find a single conductor size that has an ampacity equal to or greater than the combined ampacity of the parallel conductors. Once you have determined the equivalent conductor size, you can use NEC table 250.122 to determine the minimum size of the equipment grounding conductor. Now, let's address the specific question about using a 2/0 equipment grounding conductor. Whether a 2/0 equipment grounding conductor is sufficient depends on the size of the ungrounded conductors and the requirements of NEC table 250.122. To determine the appropriate size, you need to calculate the total circular mil area of your paralleled conductors. Since you're using three 500 mcm conductors, you'll multiply 500 mcm by 3, resulting in 1500 mcm. Then consult NEC table 250.122 to find the minimum size of the equipment grounding conductor required for conductors of that size. If the table requires a larger equipment grounding conductor than 2/0, you must use the larger size. It's also important to note that the equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the ground fault path is minimized, which is essential for the proper operation of overcurrent protective devices. Furthermore, NEC section 300.3b requires that all conductors of a circuit, including the equipment grounding conductor, be installed in the same raceway. This requirement helps to minimize inductive reactance which can impede the flow of fault current. In summary, the requirement to install an equipment grounding conductor in each raceway containing parallel conductors is based on the need to provide a low impedance ground fault path and to comply with the NEC. Ignoring this requirement can create a dangerous situation that could result in electrical shock, fire, or equipment damage. To reiterate, for your specific setup with three sets of parallel 500 mcm conductors in three separate pipes, you absolutely must run an appropriately sized equipment grounding conductor in each of those three pipes. This is not optional and it is a fundamental safety requirement. Now let's explore some of the common misconceptions and potential issues that arise when dealing with equipment grounding in parallel conductor systems. One common misconception is that if the neutral conductor is not switched, then the equipment grounding conductor requirement can be relaxed. This is absolutely not the case. The equipment grounding conductor is required regardless of whether the neutral conductor is switched or not. The equipment grounding conductor is there to provide a path for fault current, and its function is independent of the neutral conductor. Another potential issue is the improper sizing of the equipment grounding conductor. As mentioned earlier, the equipment grounding conductor must be sized based on the equivalent size of the parallel conductors. It is not sufficient to simply use the same size equipment grounding conductor that would be used for a single conductor of the same ampacity as one of the parallel conductors. The equipment grounding conductor must be sized to handle the potential fault current that could flow through the entire parallel conductor system. A third potential issue is the improper installation of the equipment grounding conductor. The equipment grounding conductor must be securely connected to the equipment grounding bus in the electrical panel and to the metal enclosures of any equipment served by the circuit. Loose or corroded connections can significantly increase the impedance of the ground fault path, which can impair the operation of overcurrent protective devices. Now let's discuss the different types of equipment grounding conductors that can be used in parallel conductor systems. The NEC recognizes three types of equipment grounding conductors. Firstly, a wire-type equipment grounding conductor. Secondly, a rigid metal conduit or intermediate metal conduit. And thirdly, a metal cable tray system. A wire-type equipment grounding conductor is the most common type. It is typically made of copper or aluminum and is sized according to NEC Table 250.122. When using a wire-type equipment grounding conductor in a parallel conductor system, it is important to ensure that the conductor is properly supported and protected from physical damage. Rigid metal conduit or intermediate metal conduit can also be used as an equipment grounding conductor. When using conduit as an equipment grounding conductor, it is important to ensure that all conduit joints are properly tightened and that the conduit is securely connected to the equipment grounding bus in the electrical panel and to the metal enclosures of any equipment served by the circuit. A metal cable tray system can also be used as an equipment grounding conductor, but only if it meets the requirements of NEC Section 392.60. This section specifies the construction and installation requirements for cable tray systems used as equipment grounding conductors. In addition to the NEC requirements, it is also important to follow any applicable local codes and regulations. Local codes may have additional requirements for equipment grounding that are more stringent than the NEC requirements. For example, some local codes may require the use of a supplemental grounding electrode system in addition to the equipment grounding conductor. It is always best to consult with a qualified electrical inspector or engineer to ensure that your equipment grounding system is in compliance with all applicable codes and regulations. Now let's consider a scenario where you have a long run of parallel conductors. In this case, it may be necessary to increase the size of the equipment grounding conductor to compensate for voltage drop. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end of the circuit. Voltage drop can be caused by the resistance of the conductors and the impedance of the circuit. When there is significant voltage drop on the equipment grounding conductor, it can impair the operation of overcurrent protective devices. To compensate for voltage drop, you can increase the size of the equipment grounding conductor. The amount of increase will depend on the length of the run, the size of the conductors, and the amount of current flowing through the circuit. There are several online calculators and software programs that can help you determine the appropriate size of the equipment grounding conductor for long runs. Another important consideration is the type of grounding electrode system used in your electrical system. The grounding electrode system is the connection between the electrical system and the earth. The grounding electrode system is used to provide a low impedance path for fault current to flow to ground. The NEC recognizes several types of grounding electrodes, including firstly, a metal underground water pipe, secondly, a ground ring, thirdly, a rod or pipe electrode, and fourthly, a plate electrode. A metal underground water pipe is the most common type of grounding electrode. If you are using a metal underground water pipe as your grounding electrode, it is important to ensure that the pipe is in direct contact with the earth for at least 10 feet. A ground ring is a continuous loop of bare copper conductor that is buried in the earth. A ground ring is typically used when a metal underground water pipe is not available. A rod or pipe electrode is a metal rod or pipe that is driven into the earth. A rod or pipe electrode is typically used when a metal underground water pipe or a ground ring is not available. A plate electrode is a metal plate that is buried in the earth. A plate electrode is typically used when a metal underground water pipe, a ground ring, or a rod or pipe electrode is not available. The type of grounding electrode system that you use will depend on the soil conditions and the availability of grounding electrodes. It is important to consult with a qualified electrical inspector or engineer to determine the appropriate type of grounding electrode system for your electrical system. Finally, it is important to periodically inspect and test your equipment grounding system to ensure that it is functioning properly. A visual inspection should be performed to check for loose or corroded connections. A ground resistance test should be performed to measure the impedance of the ground fault path. If the ground resistance is too high, it may be necessary to make repairs to the equipment grounding system. In conclusion, proper equipment grounding is essential for the safety of electrical systems. When dealing with parallel conductors, it is especially important to follow the NEC requirements for equipment grounding conductors. By understanding these requirements and following proper installation practices, you can help to minimize the risk of electrical shock, fire, and equipment damage. Remember to consult with a qualified electrical inspector or engineer if you have any questions or concerns about equipment grounding. They can provide you with expert advice and guidance to ensure that your electrical system is safe and in compliance with all applicable codes and regulations. The information provided here is for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before making any changes to your electrical system. And always remember safety first. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electrical shock and other hazards. By following these guidelines, you can help to ensure the safety of yourself, your family, and your property.